In the previous session, we have seen how the existence of the core is proved and what are some basic properties like densities, temperature, velocities of the seismic wave. And also we had some idea on the composition, or rather broad composition of the core by measuring the properties of meteorites, especially the iron meteorites. So overall we know the core is dominantly made up of an alloy of nickel and iron. But there are certain observations that reveal, though the most dominant component of the core, both the inner and the outer, is iron and nickel, but a core made up of purely iron and nickel does not match with some other properties of the core. What we will do now, we will inspect the different lines of evidence that suggest, in addition to iron and nickel, the core is bound to have some lighter element, lighter in the sense of density. There are three major lines of evidence that suggest that the core has lighter elements in addition to nickel and iron. These three lines of evidences are the geochemical affinity of elements, the abundance of certain elements compared to that in the extraterrestrial bodies like in the meteorites, and third, the heat budget of the core. First, the geochemical affinities of the elements. This is a property that determines which elements will be more prone to be associated with another element. For the study of core, two groups of such elements become very important. One group of elements is called siderophile element. It means the elements that have affinity to stay with iron. The other types of elements that also have some bearing on our understanding of the core are the lithophile elements. These elements are such they always try to remain with silicon to form silicates, and the mantle part of the earth is the main repository of the lithophile elements. The interesting part of the division between lithophile and siderophile element is that, given the opportunity, the siderophile elements will try to remain and make alloy with iron, whereas the lithophile elements will try to make compositions dominated by silicon and oxygen, and we call these things as silicates. The partitioning between the mantle and the core of these elements help us to understand what are the major elements that can be present in addition to nickel and iron in the core. The major siderophile elements among them are gold, platinum, iridium, tungsten, chromium and vanadium. All it indicates that, given the liberty, these elements will try to concentrate where there is huge amount of iron. They will prefer to stay with iron, forming alloys. Now what we have been seeing for the case of the core, because it is made up of nickel and iron, and because earth has these elements like the siderophile elements, so if there is a situation created in the past that these siderophile elements, given a choice, they will move towards iron and nickel, thereby concentrate in the core. The second line of evidence is the discrepancy in the abundance of certain elements between the earth's core and that of the meteorites. It has been found that had the entire core made up of iron and to some extent nickel, then its density, especially that of the outer core, should have been 10% higher. This calls for presence of some lighter material in the outer core. Chief candidates for these lighter materials are sulfur, silicon and oxygen. The reason for choosing these three things are that these elements, sulfur, oxygen and silicon, are found to be present in chondritic and stony iron meteorites. These meteorites contain two compounds. One is made up of iron and sulfur, a mineral called troilite, which is not found on the surface of the earth. Another composition, iron oxide FeO, called woostite, which is also not found on the surface of the earth. By analogy with these meteorites, it is now believed that the core of the earth contains, in addition to iron, some oxygen and some sulfur, as is indicated in the two types of meteorites. Another interesting comparison between the carbonaceous chondrite meteorites and the core is that the carbonaceous chondrites are believed to be very similar in composition to that of the Earth's mantle. But the carbonaceous chondrites contain 7% more silicon when compared to the mantle. So, mantle has a deficit of 7% of silicon. One of the solutions to this silicon deficiency in the mantle is that this silicon went into the core. So, this kind of proves, though in a very indirect way, using the comparison between the chemistry and the geochemistry of the meteorites and that of the known chemistry and geochemistry of the core, that core contains some lighter element. The third lines of evidence that suggests that core might have some lighter elements as light as potassium is its heat budget. As we have discussed in the earlier session, that core is the chief supplier of heat to the earth, and core retains some portion of the heat, that is the primordial heat formed during the accretion of the planet earth. One calculation shows if that is the only source of heat that the earth has, that is the core supplying the heat, at the rate the core is losing heat, and if we think that core has formed about 3.8 billion years ago, for which we will be discussing in the later section, then the core should have been much more cooler than it is now. The heat budget of the core, when tried to interpret it in terms of presence of lighter elements, clearly indicates that one needs to have an additional source of heat inside the core. The easiest way out of this problem is to generate some heat in the core, which is not primordial heat, by the process of radioactive decay. So, if some radioactive elements are put into the core, the decay of these radioactive elements can keep the core hot enough. One prime candidate for this radioactive element is potassium. Potassium is present with a concentration of 240 parts per million in the mantle. It has been calculated, if the same concentration of potassium, that is 240 parts per million, is introduced into the core, the potassium, because of its radioactive element and because of its decay, can generate enough heat to maintain the temperature of the core. Now, by comparison with the carbonaceous chondrite meteorite, it has been found that the mantle is also having a shortage of potassium. So, if this potassium is extracted from the mantle and put into the core, the problem of the heat budget does not remain anymore. So, we see now from the three different lines of evidence that core not only contains nickel and iron, but it contains some other elements like, for example, sulfur, silicon, oxygen, and definitely some radioactive elements and possibly potassium.
Please watch next part of the program, Core of